Thanks so much for joining today. I just want to do a quick introduction for those of you that don't really know who EAC is. So we help companies design, manufacture, connect to, and service their products. We also are a solution partner of PTC's and have been since about 2001. We're also the leading PTC windshield global services provider and have been for over 15 years. And along with that, we are also part of PTC's exclusive service advantage program. So the goal of this presentation today is to show how simulation is paired with mechanism dynamics option and behavioral modeling and how it can improve your quality, reduce product development costs, and accelerate your product innovation. By using these products, engineers can make more informed design and development decisions, identify and resolve design flaws early in the design process, use analysis early and often to verify and optimize design integrity, and also mitigate risk of product failure. I'll now hand it over to Todd, and he's going to show how these products work together.
All right, thanks, Jenny. So my name is Todd Kraft. I'm a technical account manager here at EAC, and my plan is to go through about 7 or so examples to show you how you can use behavioral modeling, mechanism dynamics, and also mechanism design, and also simulate, and how they all work together inside of PTC's products. Before I start though, I'd like to show you just a simple behavioral modeling problem. This is because a lot of people haven't seen behavioral modeling before. So my goal here is this little bracket is going to saddle a little tube. So we want to mirror the geometry like this, and I want this these two walls to be flat against the tube. Okay, so what I need to do in that case is I need to make this angle a certain angle so that it will, be flat there. I don't know what that number is though. I can't just make it 45 or 90 because there's like another angle there. So what people typically do is they go ahead and make a measurement, and they say, well, I want this surface here to this surface here, this plane right there. Is it really at 0? That's impossible. Did I really get that perfect? Okay, so no, it's not. That's an angle, I'm sorry. Angle is 16 degrees. Okay, so I'm going to save that, okay, and just leave it on the screen there. And then what I can do at that point is go ahead and change that again. And this is what people typically do is I want to try and get that to 0, and I don't really know the number, but I'm going to keep on trying, and it's somewhere around 34 looks like, but I'm not exactly sure. I want it to be exact. So what behavioral modeling can do for you in this case is get that number for you. So let me turn that little saved analysis off. Let's just blow that away. And under the analysis tab, and I can say, again, make that measurement between that surface and that surface. And this time, I'm going to save that as a feature, okay? I'll call it angle. Now it's in my model tree as an angle. So now that it's in my model tree, I can go ahead and solve for that under the feasibility button here. The feasibility optimization. Optimizations when you don't know the answer, you want behavioral modeling to find it. Feasibility is when I know the answer and make it happen. So the angle I want to be 0, and then the dimension to change is going to be that same angle there at 20 degrees. And it's somewhere between, I don't know, 10 and 45. I have to give it a range, okay? And I want it to be 0. I don't want it to be 0.1. So under the preferences here, I can change this to be 0.001 convergence percentage. Okay, that's just going to be an accurate answer. I say compute, and then it goes ahead and let's see, I want this to be different. I think I made a mistake here. I want the angle to be 0. Okay, my fault. Now I say, I read down there, it said the original model is feasible, the distance is 0 already, but I want the angle to be 0. So I say compute again. This time it's 34.54. A feasible solution has been found. I hit close. It's changed the geometry, just wants to confirm that. And now we have that information on that little angle here is exactly 0.000000. Great, that's what I have. So it solved a problem for me. So now when I go ahead and mirror this over, it's going to give me that perfect 2 planes there. Okay, so that's a quick example on behavioral modeling that maybe a lot of people aren't aware of. Some licenses come with behavioral modeling, some don't. Sometimes it's an extension you add. So that's the first example. Let's go ahead and show you one more because this one is really cool. I like this one. I've got these 3 parts here. This is a manifold. It's a the water cooling of a supercomputer. We have these 2 plates on the top and bottom, and the blue represents the inside. Okay, so I'm just going to open up the blue. This is the water, the coolant going through the manifold, and I'm going to do what's called a user-defined analysis. Okay, so this is not a really well-known tool inside of behavioral modeling. I can say user-defined analysis is right there. So, but first thing you do is you always make what's called a field point. So it has to start with a field point. I'm just going to pick a field point and place it on that edge right there. Okay, and then I want to make a plane through that point and parallel to that plane over there. Okay, so now we have that plane in green right there, and now we want to do a cross section of that plane, and we want to make this a feature because we want to measure the cross section area along the entire length of this coolant, so we know that it has a cross section area that we're happy with. Okay, so now we've got the point, we've got the datum plane, a construction geometry, and we've got a section property here. Okay, and if I go to there, the feature, you can see when I make a feature, I have these resultant parameters, and these are useful for plotting stuff later or solving stuff later. Okay, so that's a really important thing here. And then we're going to go ahead and group these. And now we can click on user-defined analysis. Okay, so a UDA has a field point that starts with. It has some stuff in the middle, doesn't matter what it could be, but then it ends with a feature, a behavioral modeling feature. Okay, so when I click on UDA, it recognizes that local group, great. And then I can plot back the cross-section area, and I'm gonna do like 100 points. I want 100 data points. I click on compute, and bam, there's my entire graph. This is my, where did it go? This is my entire graph of the cross-sectional area along this. And actually what it does is it puts the graph on the model as well, which is awesome. Okay, kind of overlays it like that. So this is the same graph up here, it's just kind of scrunched together. All right, so that's what I wanted to show you on a UDA. Now what happens as well, this is really, really awesome, is it will also say add a feature. And then I can hit OK. And what it will do as the feature is, I think I have to go over here and say edit definition. It will give me a, hit compute again, looking for something here. It'll give me a minimum value and a maximum value. And those are things I can drive upon later if I want to. I can have it change geometry and not have it be higher than 700 and have it solve for me, or not have it be less than 200 and solve for me. Okay, so that's a little bit more about those minimum and maximum things that result in parameters. Okay, so that's a little bit about behavioral modeling. There's one more thing in behavioral modeling I have to show you because it's going to play a role later in an example I'm going to do, and it's called the multi-objective design studies. Okay, here's a simple example. Under the analysis menu, there's a what's called a multi-objective design study. Okay, so we're going to use that in a little bit here. But first I want to show just a quick little feasibility and optimization. I'm going to say let's right here on my screen I have these 3 circles that are extruded, and the red area is the we're gonna stamp out that area. Okay, so the red area, if you stamp out those 3 circles, you get resulting red area that's scrap. Okay, but then we also want to put those 3 circle extrudes into a box. Okay, so we want to minimize scrap, but we also want to minimize the size of the box that these are going to lie flat in. Okay, so we have 2 goals: minimize area and minimize the perimeter of the box, those are 4 edges. Okay, so let's go ahead and say our dimensions to change in this case are this 7 and this 20. Okay, and those can go between 5 and 15. We'll give it some ranges on 15 and 24. Okay, and then we're going to say let's minimize the area, and then it'll go ahead and solve for us. And when you minimize the area of the scrap, it wants to make it really tall. Okay, let's undo that. And when you minimize the perimeter, say compute here, it wants to scrunch it down like that to make the smallest box possible. So we have 2 criteria that are kind of fighting each other. Okay, so let's undo that. So now what we can do is we can do a multi-objective design study right there. And we can go ahead and click on new, and we can click on that one. It's going to give us our table. We'll pick the same circles, same things here. We have to just redo this 5 to 15 and then 15 to 24. And then hit OK. And our goals should be right there. They're still there. Okay, and now we can hit this little exclamation point, and we can say, let's build, I don't know, 200 design of experiments. And then down the bottom, it's writing those right now. It's got to 50, gotten to 100, 150, and 200 is right there. Okay, so it's done. So it's built all 200 for me. And then we can do some things like I can graph this, like the x-axis is length and y is area. Here's all the possible options it just gave us. So now we can start to look at this data and say, well, I want to be around 175 for my box perimeter, and here's the least amount of scrap, which is right there. You know, that's number, what's that, 174. So then I can go over here and I can try to find that one, or I can also derive a new table. I can derive a new table, and I can say that the max is 750, the min is 740. Maybe let's just hit OK. That's graph 2 or table 2. There's 7 of those. Okay, and then I can say, oh, this is the one I want. That's the one I like right there, the 175. Then I can show that model. There's the perfect model that just gave us, and then we can go ahead and see that those are the 2 dimensions it uses in this case. Okay, so there's a great way here, multi-objective design study. We're going to use that a little bit later when we start doing some simulation interaction. Okay, so wanted to show that to you quick because it's going to play a big role later on. All right, so those are 3 behavioral modeling examples. Let's go ahead and go to a different screen of Creo. Let's show some of the interaction between behavioral modeling and mechanism now. Let's go ahead and open this mechanism here, and we're gonna go ahead and assemble a couple of things. One is the connecting rod, and that's gonna be on a pin joint. So these two surfaces and these two, and let's put that up there. And then we'll go ahead and add the shaft up on top. This is a reciprocating saw. It's a good idea to put it pretty close to where it's supposed to be because it'll snap into place. This is going to be a slider joint here and there. And then we have a couple of planes that we're going to use. I want this end plate. They're hidden, so I'm going to go ahead and just find them. Other one is hidden as well. You can see those two planes right now, green and red there. There's our slider now. Okay, so it slides in and out. It does not rotate though. We want to add one more though. We're going to add a bearing joint on that point and this axis. Great. Now we should be able to go to mechanism and just let it run around one revolution here. Okay, we can play that back, and now everyone knows how a reciprocating saw works. Okay. There's our input shaft in the bottom. There's our wobble joint. The wobble joint plays a big role because the larger the wobble, the more of a translation you get up on top. Okay, so let's go ahead and minimize that. And we're gonna close mechanism or go out of mechanism. Now, here's the magic. So now that I ran my mechanism, I can now integrate that with behavioral modeling. So all I have to do is start making some behavioral modeling features. Let's turn my features on here in the assembly. And I can start to do a analysis and measure between that surface and that surface. So it says it's 4, okay. Not sure why it's down there. It says it's 4, and we want to make that a feature. And just call it distance. It's now a behavioral modeling feature. It's in my model tree. It's right there. Great. Now we can do what's called a motion analysis. I want that distance to be measured through the entire motion that I had ran earlier. So I click on distance and I hit run, and there's my graph. Okay. There's my graph. And I can see it goes from 4 up to about 4.45 down to about 3.54. Okay, so great. Now I can make this a feature. Say add a feature, call it motion. And as a result of this motion analysis, if I go to information, I have a min distance and a max distance. So those two numbers are captured. So what I can do next is a behavioral modeling feature that's a relation, okay? And I'm gonna say the total stroke equals the difference between those two values. Pick on that motion, the min, the max, and I'll just go ahead and copy that, minus the min. I'll just do it the easy way here with min. There we go. Hit OK. And OK. And now if I do information on that one, not rename, do information on that one, it is now 0.9058. Awesome. So it's less than an inch. And now I can do all kinds of fun stuff. I can do sensitivity studies. I can say, if I change that wobble angle, right there, that's 11 degrees, between 4 degrees and 14 degrees, plot back the total stroke and build 10 of them. And then boom, I get it to run. It's changing the angle and running it in mechanism for me at the same time. So I can see my total stroke is between 0.33 and 1.14. So awesome. So now I can take that information. I can say, well, let's okay. I know what's possible now. Let's go ahead and say that the total stroke is at, I don't know, 1.05, and the dimension to change is that one. It's a higher dimension, so oops, not 1, 14. And then I like to just change my preferences here. I wish this was a default. I could change it, but I want exactly 1.05. So I'm going to change my convergence to a lower number, 0.001. Hit compute, and it'll change that wobble angle to give me exactly the stroke I want. It says it's found it. I hit close. I confirm that some geometry changed. Go over here to my information and feature, and there's my 1.050000. So CAD is used a lot just to make a drawing, but CAD can also be used with behavioral modeling to solve the kind of problem you're looking to solve. So that's a quick example on mechanism and behavioral modeling. I've got a couple more. I'm just going to open this part by itself here, this shaft here. Let's take this into Simulate by itself, and let's go ahead and assign a material. Let's just say steel. Great. And let's hold it fixed over here. Let's put a force over here. I'm just making stuff up here. I don't know, 20. Is that the right direction? Yeah, it's good. Okay, so we've got 20 pounds of force that direction. And let's just solve that. Yeah, sure. So it's solving it. Now, if you know by default, what happens in Simulate is it solves for all kinds of stuff. It solves for all these measures, okay? So from beam bending to displacement, rotational stresses, strain energy, it solves for all these values for you. And every one of these dimensions or values can be used as a behavioral modeling parameter. Okay, so I'm gonna just close it. I could also make, new ones on the measure. I could make some new user-defined measures too that I can pass back to Creo as well. But I'm gonna show you how the integration works. I'm just gonna close Simulate. I have to run a simulation ahead of time just to define the analysis, because inside of Creo, to integrate with Simulate, I go to Analysis, and there's my Creo Simulate button. So I hit Next. It finds the analysis. I click on Compute, and it's really nice. It warns me this might take a while, but that's fine. I know it takes a while. It doesn't take very long. So then it goes out and solves it, and then it comes back to me with these different parameters. Okay. So I hit close, and then I can say I want these parameters, yes or no. It's up to me. I wish I could select them all at one time, but I can get all those. I can define if I want those parameters, yes or no. I hit OK, and now I have this behavior modeling feature here in my tree. And then I can run sensitivity studies on this. I can say let's change this length here from 4 to 7. I don't know, and then plot back the max displacement magnitude. Okay, let's just build like 3 of them. And it'll regenerate at 4, and then I guess it's gonna go to maybe 5.5 and then 7. And at this point, people that are savvy on the phone that have ran Simulate before are going, well, this is no different than what I can do as a sensitivity study inside of Simulate. Why do I have to go back and use behavioral modeling? And that's a great question. And for this example, you don't have to. However, by looking at functional answers like displacement, I can combine structural results with geometric results. Now think about that for a second. I can do things in Creo like surface area, like center of gravity locations, volume, any kind of measurement I can make with this analysis menu inside of Creo in general. I can now combine those kind of geometric parameters with functional parameters that I get over on the Creo Simulate side. So I can optimize a heat sink, for example, or I can optimize the modal frequency of a component. Okay, try doing that without this. That's a really, so you can make geometric changes to capture functional and geometric changes or geometric parameters in your model. Okay, so that's a quick example of how you integrate Simulate with Creo. So let's go ahead and close out of here. And I think this next one I have already teed up here. Let's see. Nope, get rid of that one. Okay, so let's talk about mechanism dynamics a little bit too. So before I was running a mechanism design problem, I didn't care about forces at all. I just cared about the stroke of that mechanism. But I could have also captured reaction loads and optimized those too. You can optimize based on those reaction loads. You can have linkages change, location of linkage connectors change. Those are all any dimensions on the table when it comes to behavioral modeling and mechanism dynamics. Okay, so here's a mechanism dynamics problem. I'm gonna go ahead and just go to mechanism here, and I'm gonna run this dynamics problem. We have just some simple pin joints down here, a ball joint there. That's for redundancy. And then we have a external force opposing that action. So we can look at the measures, get our forces. That's all great, There's our forces. But we want to pass those to Creo Simulate. So I can do analysis, and right here it's called use in simulation. I pick on the component that I want to capture the loads with. That's the body. I pick on the component that I want to store those values into, and then I can choose what values or which ones get passed. There's all the ones that are there. There's some really tiny moments on there. I'm going to ignore those, ignore the angular velocity, and also ignore gravity. Just those three forces are left over, just the force on here and the two inside the pinholes. And now we can close here and open this model by itself. And now when I take this model into Simulate, I can hit loads, and there's my mechanism load. And there's my three forces. I hit OK, and those three forces pop into place as they're called TLAPs, or total loaded at a point forces. So they're loaded on the right point, but I have to tell it the geometry. I'll pick those surfaces there. So I have to come in here and just double click that and say, well, these surfaces are the ones it's being used on, and respectively that one's as well. So there's now, they're all valid. And then now I think I have a material. Yeah, I do. The materials are already applied. It's aluminum. And then I go to my analysis, do a new static analysis. And now I don't have a constraint, right? It's really kind of floating around. I can just use inertia relief, which is awesome when you use mechanism loads, because I don't have to constrain it. and it's going to give me equal and opposite accelerations in the locations of the forces. So I'll check inertia relief, hit the green flag, and it will mesh it and solve it. And then I go to results, and let's just click on this stuff here. There's our enforced or our exaggerated stress result, okay? So that is a quick example of integrating mechanism dynamics with Creo Simulate. All right, so the last example I have to show is next. And that's this one here. This one's a unique one. This is from the SAE car. This is, I believe, the Indy car, not the Baja one. And this is a curve example. And if I go into simulate, this has been simulated with a bunch of beam elements and some tubes down here. Okay, we got some tubes, some square tubes and some circular tubes. Okay, and we got the little outline of the person in there in green in there. Okay, so this is the beam example. Now, what we're going to do at this point is that there's inside of this example, we're going to run a beam analysis, but there's a measure in here, and it's called rigidity, and it's a computed measure of the right and left reaction loads, and it's got some gravity in there, and it's going ahead and it's going to give us a computed value called rigidity. And this is an important value to know once you get outside of Simulate to help drive some changes in the design. So I have a PowerPoint here to show you here. So this is an educational model from university, and what we want to do is all those tubes have specific dimensions. They're discrete variables, we'll call them. There's 11 independent tubes with 9 different configurations, 3 different diameters and 3 different wall thicknesses. So what you can do is when you define these beams with real numbers, you can parameterize those beams. Okay, I can call them beam 2 radius outer, beam 2 radius inner, okay, and so forth for the tubes and the circles. And then I can make a bunch of parameters. Okay, I can make all kinds of parameters inside of Creo. And then I can also do some relations, and I can have it say if the tube stock 1 equals 1, then make the outer radius this and the inner radius this. If it equals 2, so I can have some if-then logic to control those dimensional values. And then I can take those into a multi-objective design study. I want to build a whole design of experiments with hundreds of different possible combinations of these discrete variables. So the automatic method I showed you earlier with that packaging example with the scrap and the size of the box, that was an automatic method where I said minimize something or maximize something. But you can also do a manual method. You can declare, I want tube stock 1 to be 1, 2, 3, or 4, and I can tell it all those different combinations. And what happens is it'll go ahead and build all the prototypes for you. So I built, for that car, I built 1,944 prototypes in 2 hours. And then I can graph the mass versus that user-defined measure, that rigidity. And then I can find the best one. If I have a rigidity value I'm trying to look at, I can find the best possible mass for that by looking at all the combinations of all the tubes in the entire model. So if I look at all the possible ones, it's over 46,000 prototypes. So I'll show the way so this is the best one here. built on those 1944 prototypes. Let's go ahead and just show the logic here. Again, we have already in Simulate, it's called a frame rigidity analysis. So on the Creo side, we can run a multi-objective design study. There's our Simulate feature there in the model tree on the left side there, right there. I'm gonna go ahead and open a saved one already. It's right there, study 2. And there's those 1944 examples right there. There's all of them. But then you can go ahead and also, say, I want the mass between those two numbers and the rigidity between those two numbers. Or I could minimize and maximize with Pareto as well. But I'm gonna say constraints, hit OK, there's my 24. And, get the best possible answer. I'll just pick up this one and say show the model. And there's the model right there. So this is pretty impressive. You can have Creo Simulate working with behavior and modeling to have it build as many prototypes as you want. Okay, so with that, I've gotten to the end of my last example, and I can take questions if there's any questions in the queue.